Mars was doomed to desiccation by its small size, a new study suggests. Thanks to observations by robotic explorers such as NASA's Curiosity and Perseverance rovers, scientists know that in the ancient past, liquid water coursed across the Martian surface. The red planet once hosted lakes, rivers and streams, and possibly even a huge ocean that covered much of its northern hemisphere. But that surface water was pretty much all gone by about 3.5 billion years ago, lost to space along with much of the Martian atmosphere. This dramatic climate shift occurred after the red planet lost its global magnetic field, which had protected Mars' air from being stripped away by charged particles streaming from the Sun, scientists believe. But this proximate cause was underlain by a more fundamental driver. According to the new study, Mars is just too small to hold onto surface water over the long haul. Mars' fate was decided from the beginning, study co-author Kun Wang, an assistant professor of Earth and Planetary Sciences at Washington University in St. Louis, said in a statement. There is likely a threshold on the size requirements of rocky planets to retain enough water to enable habitability and plate tectonics. That threshold is larger than Mars, the scientists believe. The study team, led by Zhen Tian, a grad student in Wang's lab, examined 20 Mars meteorites, which they selected to be representative of the red planet's bulk composition. The researchers measured the abundance of various isotopes of potassium in these extraterrestrial rocks, which ranged in age from 200 million years to 4 billion years. Isotopes are versions of an element that contain different numbers of neutrons in their atomic nuclei. Tian and her colleagues used potassium, known by the chemical symbol K, as a tracer for more volatile elements and compounds, stuff like water, which transitions to the gas phase at relatively low temperatures. They found that Mars lost significantly more volatiles during its formation than Earth, which is about 9 times more massive than the red planet. But Mars held onto its volatiles better than did Earth's moon and the 329-mile-wide, 530 kilometers, asteroid Vesta, both of which are much smaller and drier than the red planet. The reason for far lower abundances of volatile elements and their compounds in differentiated planets than in primitive indifferentiated meteorites has been a long-standing question. Differentiated refers to a cosmic body whose interior has separated into different layers, such as crust, mantle and core. The finding of the correlation of K isotopic compositions with planet gravity is a novel discovery with important quantitative implications for when and how the differentiated planets received and lost their volatiles, Lauder said. The new study, which was published online September 20 in the journal Proceedings of the National Academies of Sciences, and previous work together suggest that small size is a double whammy for habitability. Bantam planets lose lots of water during formation, and their global magnetic fields also shut down relatively early, resulting in atmospheric thinning. In contrast, Earth's global magnetic field is still going strong, powered by a dynamo deep within our planet. The new work also could have applications beyond our own cosmic backyard, team members said. This study emphasizes that there is a very limited size range for planets to have just enough but not too much water to develop a habitable surface environment, co-author Klaus Mesger, of the Center for Space and Habitability at the University of Bern in Switzerland, said in the same statement. These results will guide astronomers in their search for habitable exoplanets in other solar systems. That surface environment disclaimer is an important one in any discussion of habitability. Scientists think that modern Mars still supports potentially life-supporting underground aquifers, for example. And moons such as Jupiter's Europa and Saturn's Enceladus host huge, possibly life-supporting oceans beneath their ice-covered surfaces.